Let us start off with our presentation, flight control, with longitudinal control, elevator effectiveness, and wind tunnel model. Flight control. There are three primary aerodynamic controls: pitch control, yaw control, and roll control. Pitch control is achieved by changing the lift on either a forward or aft control surface by flapped portion of tail called elevator. Yaw control is achieved by deflecting on vertical tail called rudder, and roll control is achieved by deflecting small flaps located outward towards the wingtips called spoilers. Roll movement can be achieved by deflecting just one spoiler at a time. Elevator effectiveness. An aeroplane pitching attitude can be controlled by either aft tail or forward tail canard. The influence of elevator of an aft tail on the pitching moment is shown in the curve here. This curve shows the influence of the elevator on the pitching moment curve. The elevator does not change the slope of pitching moment curves but only shifts them so that different trim angles can be achieved. When elevator is defected, lift and pitching moment changes. So we have change in CL, that is coefficient of lift, and delta E is the elevator effectiveness. So we have delta CL is equals to CL delta E into DE, where CL delta E is equals to DCL by D delta E, where CL is equals to CL alpha into alpha plus CL delta E into delta E, and alpha is the angle of attack. On the other hand, the change in pitching moment acting on the aeroplane can be written as delta Cm is equals to Cm delta E into delta E, where Cm delta E is equals to dCm by d delta E. The stability derivatives Cm delta E is called elevator control power. The larger the value of control power, the more effective the control is in creating the control moment. Adding delta Cm to the pitching moment equation yields Cm is equals to Cm naught plus Cm alpha into alpha plus Cm delta E into delta E. The derivatives Cl delta E and Cm delta E can be related to the aerodynamic and geometric characteristics of the horizontal tail in the following manner. Change in lift of the aeroplane due to deflecting the elevator is equal to the change in lifting force acting on the tail. So delta L is equals to delta LT, where we get delta CL is equals to ST by S efficiency delta CLT is equals to ST by S efficiency dCLT by d delta E into delta E, where S is the reference wing area and ST is the reference wing area of the tail. dCl by d delta E is called the elevator effectiveness. The elevator effectiveness is proportional to the size of the flap being used, as an elevator can be estimated from the equation. So we get dCLT by d delta E is equals to dCLT by d alpha t into d alpha t by d delta E is equals to CL alpha t into tau. The parameter tau can be determined from the figure here. The increment in aeroplane's pitching moment will hence becomes delta Cm is equals to negative of tail volume ratio, that is VH, into efficiency of delta CLT is equals to negative of tail volume ratio into efficiency by the elevator effectiveness into delta E. Or we can also write it as Cm delta E is equals to negative of VH efficiency dCLT by d delta E is equals to negative of VH efficiency CL alpha t into tau. The designer can control the magnitude of the elevator control effectiveness by proper selection of the volume ratio and the flap size. The wind tunnel model, which says the area and the chord of the wing are 0.1 meter square and 0.1 respectively. Now assume that the horizontal tail is added to this model. The distance from the elevator center of gravity to the tail's aerodynamic center is 0.17 meter. The tail area is 0.02 meter square. The tail setting angle is 2.7 degrees. The tail lift slope is 0.1 per degree. And from the experimental values, we have the downwash angle as 0 and downwash angle with respect to the angle of attack as 0.35. These are the parameters that we will be using for the further calculation of different chapters. Let us move on to elevator angle of trim in the next session. Thank you.